Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at forces and pulleys so we can answer questions from exercise 10F. So we're going to look at two main types of pulleys and we'll show both of those in two different examples here. We're going to be using simultaneous equations to solve these pulleys type questions, so be prepared for that. So here's the first type of pulleys question. So particles P and Q, masses 2m and 3m, so m is just an algebraic term here, are attached to ends of a light inextensible string. The string is then passed over a smooth, fixed pulley, and the masses hang in a taut string. The system is released from rest. Find the acceleration of each mass, find the tension in the string in terms of m, and the force exerted on the pulley by the string in terms of m as well. Find the distance travelled by Q after the first 4 seconds, assuming that P does not reach the pulley. So that is probably going to link in with SUVAT at some point. Let's have a look at the diagram. So what we've got effectively is a pulley system that's attached to the roof with the string, the taut, inextensible string that's light, going over the pulley here, and on either side of that pulley system we've got masses of 2m and 3m. Now just from visualizing and imagining the problem here, we can defer that the mass with 3m is going to fall and the mass of 2m is going to be raised up because the 3m is heavier than the 2m. So we're going to assume here that acceleration is going to go downwards for Q and upwards for P. So what do we need to add onto our forces diagram? So we've got 2mg going downwards at the 2m mass. We've got 3mg acting downwards on the Q particle. We'll have tensions at the joining points of the string and the particles, equal tension. The general rule is that if it's the same string that's going over the pulley, and it's not two different pieces of string attached to a pulley somehow in another way, which we don't see at this level here, it's the same tension throughout the system. And the point at which the string meets the pulley system as well will have equal and opposite tension as well. So really it's a little bit further up the string up here, but we'll draw it lower down so it's more visible to us. The heavier particle will go downwards, so acceleration is down for Q and up for P. And sometimes we have to set up two equations from equations P and Q. So looking at all the forces and acceleration attached to particle P. So that's going upwards, so the upwards direction is positive here. So for F equals ma, there's tension on the particle P that's going upwards. We have the weight, which is 2mg going downwards in opposite direction to acceleration. And then on the other side, this is equal to 2ma. So 2m being the mass and a being the acceleration. So that's one simultaneous equation that we've got here. The second simultaneous equation comes from Q, so let's look at the forces attached to Q then. So we'll have downwards as the positive direction. So that's 3mg going downwards, and T is in the opposite direction this time, equals 3ma. And we've got these two simultaneous equations here. Now you can rearrange to solve for T and then substitute in on the other side, but actually in this specific situation here, the easiest thing to do with these two simultaneous equations is to add them together because we have one positive T and one negative T. So in this case here it's 3mg add minus 2mg, which just gives you a single mg, and then 2ma add 3ma gives me 5ma. So in this case here, a is going to be 1.96. Cancelling out the m's on both sides, dividing through by 5. So yeah, a is 1.96. So 1.96 meters per second squared. Part B is find the tension in the string in terms of m. Well, let's just substitute the value of a back into one side of these of either one of these equations. So substitute in a equals 1.96 and we get 23.52 lots of m. So as the value of m increases, you can imagine the tension in the rope will increase as the weight gets larger. So our answer here is going to be in terms of m, and when a question says in terms of m, it means that that letter is allowed in your answer. Part C is find the force exerted on the pulley by the string in terms of m. Well, at the pulley, if we look at all the forces attached to the pulley, we've got two tensions acting downwards. So effectively, it's double the tension that's acting on the pulley system there. So 47.04 m. You could have also taken your particle system as a whole, and it would just be 5 mg. Right, okay, next question here then. So find the distance travelled by Q in the first 4 seconds, assuming that P does not reach the pulley. So Q is going to drop down, acceleration is going to be 1.96, starting from rest, and T is 4, so a little bit SUVA. S-U-V-A and T, substitute all the values in, and we get S is equal to 15.7. Now the reason we had to include assuming that P does not reach the pulley here, if P were to reach the pulley and get lodged, stuck in there, then Q couldn't travel any further. So that's why we had to add that little assumption in there. But 15.7 meters is the answer to that question. Comment on any modelling assumptions used. Well, let's go through the modelling assumptions here. Light string, no mass. Inextensible string, particles move with the same acceleration. No stretching, and smooth pulley, there's no frictional force on the string, and the tension on both sides is equal. Okay, so that's how you do that type of question there, where we've got two connected pulleys over a string over a smooth pulley. What we're going to look at now is a similar problem where we've got one particle that's resting on a table and the other one that's hanging down from the table effectively. So we have two particles here, A and B, of mass 0.4 and 0.8 kilograms respectively, connected by lighting and sensible string. Particle A lies on a rough horizontal table, so there's going to be some friction there. 4.5 meters from a smooth fixed pulley which is attached to the end of a table. The string passes over the pulley and B hangs freely with the string taut, 0.5 meters above the ground. The frictional force has a magnitude of 0.08 G, so G being 9.8 meters per second squared. The system is released from rest. Find these series of questions here. So what does the diagram look like? Well, we're going to have a table. The pulley's on the end of the table. We have particle A attached to it, particle B hanging freely. B is 0.5 meters above the ground. A has a weight of 0.4 G and an R force that's acting upwards. Has a friction which is 0.08 G going to the left, because it will assume that it's travelling to the right. Tension will be at the point connecting the particle and the string. For B, there's a weight of 0.8 G hanging downwards, tension acting upwards at the point where the particle meets the string. And last but not least, the tensions that are at the point where the string meets the pulley in two different positions here and here. Acceleration is going to be going to the right, as the particle B will fall down to the ground with equal accelerations in both components. So, to answer question A, the acceleration of the system, what we're going to do is form our two simultaneous equations A and B and then solve them. So for A, if it's accelerating to the right, applying F equals ma, we're going to have tension minus 0.08 G equals mass times acceleration. And the F equals ma equation for B, seeing that A is dropping to the ground, is going to be 0.8 G take away T, which is equal to mass times acceleration. And again here you can see that we've got a negative T and a positive T. Add the equations together and they'll cancel out. So we get 0.72 G equals 1.2A. So divide through by your 1.2 and you get 0.6 G as your value for A. Now I suggest you could turn this into a decimal here, but it's going to be more accurate. It's a bit like leaving your answer in terms of pi. It's a good idea to leave your answer in terms of g, 0.6 g. Part B here is find the velocity with which B hits the ground, so a little bit of suvat. We have S equals distance of 0.5 meters from rest, acceleration 0.6 g, so let's go ahead and work out the final speed. In this case here we get 2.42, but it's worth bearing in mind, so we've got v squared equals 0.6 g, which we could use later on. The total distance travelled by A before coming to rest. So what's going to have happened then is particle B is going to have reached the floor. Particle A is going to have moved some amount so that it's at 2.42 meters per second as a velocity, and it's going to have also travelled 0.5 meters along. And in the question here it said 4.5 meters to the pulley, so hopefully it's going to be less than 4.5 meters in total distance travelled. So once B has hit the ground, there's no longer any more force that's pulling A along here. So now effectively tension is equal to 0 because B has hit the floor. It's no longer pulling that string down or effectively pulling this string along. So T here is effectively now 0 because we've hit the floor and there's no longer any more tension in this string. So the string has now become slack, but it still has some frictional force which is going to be slowing it down. So I'm expecting to get negative acceleration here. Great, minus 0.2 g is our negative acceleration or our slowing down rate. And now we apply suvat. So S equals, U is equal to 2.42, but remember 2.42 squared was 0.6 g, I think I remember that being. V is equal to 0, final speed is equal to 0 because it comes to rest, and acceleration is minus 0.2 g. So V squared equals U squared plus 2AS. Substitute in your values. Now it's a good idea here to have gone back and looked what 2.42 squared was, and then simplify what you've got at the back here, rearrange to find S, and you've got 1.5 meters. Now the total distance travelled by A before it comes to rest has to include that 0.5 meters that we initially travelled plus the extra 1.5 meters travelled after the string became slack. So the total distance here is 2 meters travelled rather than just the 1.5 when the string became slack. Alright then, so we've got two questions here for you. Here's the first one. Pause the video and try this one out. Right then, well done for having a go at this question here then. So what we have is two particles that are going over a fixed pulley and they're just both dangling down like this. We have particle A with a mass of 4 kilograms, so a weight of 4g, and particle B with a mass of 3 kilograms, so a weight of 3g. We have tensions where the particles connect to the string, and tension also where the string connects to the pulley. We're going to have acceleration going downwards for particle A because it weighs more, and upwards for particle B because it weighs less. Perfect. Question set up. Part A. Find the tension in the string. Okay, the only way I can see we're finding the tension here is to go through the acceleration and use the acceleration in one of the formulas. So, using F equals ma for particle A, it's going downwards, so we'll take downwards as positive. So 4g subtract the tension equals mass times acceleration. For particle B, this one's going upwards, so upwards is positive for this one, so t minus 3g equals mass times acceleration. And we can see here that we've got one positive t, one negative t, so cancel them out by adding the equations together. You're going to get g equals 7a, so a is equal to g over 7. And let's work that out. Well, 9.8 divided by 7, and for that we get 1.4 meters per second squared. Okay, so that's not what we're looking for. We're looking for tension though, so we'll use equation B to substitute it back in. Let's add the 3g onto the other side. So it'd be 3g add 3g over 7 from 3 times acceleration. So we'll times that answer by 3 and then add on 3 times 9.8. So we're going to get 33.6 newtons. Perfect. Part B here. So A has travelled a distance of 2 meters downwards, strikes the ground and immediately comes to rest. Part B is to find the speed of A when it hits the ground. So a bit of suvat here. Travelled 2 meters, so that's S. Started from rest, that's 0. Final speed was what we want to find. And acceleration here is going to be 1.4 meters per second squared. So in this question here, I think it's a v squared equals u squared plus 2as. So here, v squared is what we want to find. So it's just going to be 2 times 1.4 times 2, which is going to equal 4 times 1.4 equals 5.6, and then we'll have to square root that. Square root answer 2.37 meters per second. Great. Part C here is assuming that B does not hit the pulley, find the greatest height it reaches above its initial position. So what's happened here is A's dropped to the floor 2 meters, B's risen up 2 meters, and now B is going to have the same speed that A had as it hit the floor. And then it's just going to travel upwards with a string that's loosened up. So it's no longer got the tension that's pulling it down. So acceleration is now going to be different. When we plug this into suvat, we're going to get acceleration of minus g, because now effectively B is just a particle in midair with a loose string attached to it that's not doing anything, with only one force attracting it down, 3g. And if we set 3g equal to 3a, we get g equals a. So acceleration is minus g. Why have I set minus g? Well, because I'm going to set velocity as 2.37 going upwards, so I need my acceleration to go in the opposite direction. I want to find s when the final velocity is equal to 0, because it reaches a maximum height. So it's another v squared equals u squared plus 2as. And what I'm going to use, instead of using 2.37, I'm going to go back to what v squared was and use 5.6. So 5.6, we want to find v squared. No, sorry, we want to find s, don't we? Oh yeah, so that would have been fine. 0 is what v was, 5.6 is what u squared was, minus 2g s, minus because we've got the minus g over here, and it's 2 from the suvat formula. So it's going to be 5.6 divided by 2g, which is going to be some decimal number, 2 times 9.8, and that gives us 2/7, which means that s is equal to 0.286 meters. So that's how far it's travelled once the string has become loosened, but remember it's already travelled that 2 meters. So therefore total distance here, s is going to equal 2.286, and rounding that to the correct significant figures, it's going to be 2.3 meters per second. No, meters, because I've used g in my calculation. Right then, second question. So here is another one where the particle goes over the table. Pause the video and try this one out. Right, well done for having a go at this question here then. So this question here is one of these ones where we've got our fixed table and one particle that's on the table, I think this was A, so that was 5 kilograms, so weight of 5g. We'll also have R going upwards as it's resting on the table. We'll have tension attached to the string at this point here, and we'll also have a hanging particle over here, 3g as its weight. T is at the point where the particle meets the string, and also tension at the point where the string meets the pulley. So friction force between A and the table is 24.5 newtons. So we'll add that onto our diagram, going in the reverse direction. The system is released from rest. Find the acceleration of the system. So we'll fill this space in down here. So the acceleration of the system is going to be calculated by two simultaneous equations. We've got particle A here, particle B down here. So for A, it's going to be T minus 24.5. We're assuming here that we're going to accelerate downwards for B and to the right for A. So T minus 24.5 equals mass times acceleration. And for part B, it's going to be 3g minus t equals 3a. So we've got a negative t and a positive t here. Let's add these two together. So 3g minus 24.5 equals 8a. And combining these two together, we're going to get 3 times 9.8 minus 24.5 divided by 8 equals 0.6125. Okay, there we are. That's the answer to part A. The answer to part B is going to be meters per second squared. The answer to part B is going to be T equals 24.5. So I'm taking equation A here and adding on 5 lots of 0.6125. So my tension here is going to be 5 times answer, add 24.5 is equal to 27.5625 newtons. I'll probably round this off to 27.6 newtons. Part C here, find the magnitude of the force exerted on the pulley by the string. Well, let's just take a closer look at the tension here. We've effectively got the pulley system here with two tensions being applied to it. A 27.6 Newton force going this way and a 27.6 Newton force going this way. And what's going to happen is the force is actually going to be acting in that direction. So effectively what we've got, if we move this down to here, what we've got is 27.6 newtons effectively being applied horizontally, 27.6 newtons being applied vertically. So doing a bit of Pythagoras on this, we've got 27.6 squared add 27.6 squared, and this is going to equal 38.98 newtons. Let's round that off to 39 newtons in total. Great, so there we are. That's the answer for the second question for this video here. So have lots of practice on exercise 10F. They're pretty tricky questions. The more you do, the better you'll become at them, and the more you'll be familiar with these questions when they appear again in the future. Right, persevere through the difficult ones. Do have a go at answering the questions towards the end of this exercise in particular. Those are the tougher ones, the ones that are more likely to appear in an exam. Thanks very much for watching this video.